Welcome to Night Chemistry, your midnight observatory of calm. Tonight, we leave the comfort of Earth's skies and venture inward, past Venus's shimmering clouds, to Mercury's shadowed orbit, where the sun's breath becomes a river of protons. Here, vast magnetic petals drink from that invisible wind, forging helium-3, the quiet promise of clean, endless fusion. Prologue, Proton Dawn. The station drifted in the ink-black silence just inside Mercury's orbital shadow, where sunlight was not a gentle glow but a torrent of radiation. Beyond its latticework arms, vast mirrors caught the sun's breath and bent it into shimmering funnels. Streams of protons, swift, invisible travelers from the solar wind, spiraled into magnetic traps that glowed faintly in the ultraviolet. Inside those quiet coils, the seeds of a new age were forming. Helium-3, the isotope long whispered about as the key to clean, limitless fusion power. It was not mined but born. Each particle captured here had crossed millions of kilometers to reach this place, drifting from the sun's corona with a kind of ancient patience. When enough were gathered, they would fuse, not in the uncontrolled fury of a star, but under the measured guidance of human-built reactors. On Earth, such fuel could end the long shadow of scarcity. Operators moved through the station's narrow corridors with an unhurried grace, their voices calm, their instruments steady. Yet beyond the quiet hum of superconducting magnets, the sensors spoke in a different language. Minute fluctuations in the proton stream, irregular pulses hidden in the noise. Patterns that had no place in the constant wind. And somewhere on the far side of the sun-facing mirrors, the dawn was brightening into something else. Chapter 1, Solar Traps. From a distance, the station's collectors looked like a frozen bloom of metal petals, each one tens of kilometers across, tilting imperceptibly to follow the sun. Their purpose was not to reflect light but to shape the invisible tide of charged particles rushing through the void. The solar wind, mostly protons and electrons, streamed from the sun at hundreds of kilometers per second. Left untamed, it was a hazard, able to strip atmospheres, scorch electronics, and endanger human tissue. But here, vast superconducting loops generated magnetic fields strong enough to bend those streams into containment arcs. Within those arcs, protons slowed, cooled, and paired with carefully supplied deuterium to yield helium-3. The isotope was rare on Earth's surface, its traces locked in ancient lunar soil or scattered thinly in the upper atmosphere. In the confines of these magnetic vaults, however, it could be produced in purities Earth's fusion engineers once only imagined. A senior systems engineer, Commander Liz Solarin, moved among the magnet banks, her steps light in the station's fractional gravity. She spoke softly, knowing the hum of superconductors would carry her voice through the intercom to a cluster of new cadets. "Treat the proton stream as you would the sun itself," she said. "It is patient but it is powerful. You don't force it into the trap, you persuade it. Let the magnets curve its path until it settles." On her console, a readout displayed steady particle counts, green bars across the board. Yet even here in this moment of equilibrium, a ripple passed through the measurements. Liz's eyes narrowed slightly. She made a note, her voice calm, but her mind already turning over the pattern. For now, the solar traps continued their silent harvest, each loop adding its measure to the growing reservoir of helium-3. But the data suggested the wind had begun to shift. Chapter 2, Earth's Energy Hunger. On Earth, the word scarcity had taken on a sharper edge. In the early decades of the 22nd century, global power grids had grown into a patchwork of desperation. In temperate regions, brownouts came with the seasons. In hotter latitudes, blackouts could last days, forcing hospitals to ration cooling and water purification. The wealthy insulated themselves with private microreactors, sealed behind layers of corporate contracts. For everyone else, the lights flickered according to the mood of a fragile grid. The crisis had been centuries in the making. Fossil fuels, once the bedrock of human industry, were now geological relics, buried not for lack of technology to extract them, but because their extraction had already pushed the planet's climate past a point of safe return. Renewable energy sources, wind, solar, tidal, had spread wide across continents and oceans, but they still danced to the rhythm of nature's variability. Batteries and capacitors could smooth the peaks and valleys of supply, but they could not meet the unblinking hunger of cities that never slept. Fusion had been the great hope, the beacon science promised since the 20th century. But the practical challenge of containing a miniature sun on Earth proved more stubborn than the dream. Tokamak reactors and laser ignition chambers inched forward, each breakthrough shadowed by engineering obstacles that kept commercial-scale fusion always just out of reach. Helium-3 changed that equation. Unlike deuterium-tritium fusion, the easiest reaction to start, but one that produced a torrent of high-energy neutrons, helium-3 fusion offered a nearly anetronic path. When fused with deuterium, it produced mostly charged particles instead of neutrons, meaning the reactor walls would last far longer, and the energy could be converted directly into electricity using magnetic induction. In short, it promised clean, compact, and long-lived fusion plants without the crippling maintenance cycles that had haunted earlier designs. The problem was availability. On Earth, helium-3 was vanishingly rare. It existed in measurable quantities only as a byproduct of tritium decay, tritium itself being costly to produce. The Moon held deposits implanted by billions of years of solar wind exposure, but even those required massive infrastructure to extract. And in the deep atmospheres of Jupiter and Saturn, helium-3 was abundant, but so far away that any mining effort was purely hypothetical. That left the inner solar system's solar wind harvesters. The Mercury Orbit Solar Farm, MSF to those who lived and worked there, was the crown jewel. Positioned in a tight elliptical dance just shy of the sun's full glare, it caught a denser proton stream than any platform farther out. Its collectors were tuned not just to trap protons, but to shepherd them into carefully moderated collisions that yielded helium-3 as an intermediate in a proprietary catalytic process. The output was measured in kilograms per week, a trickle by mass, but an ocean in terms of the energy it could release. Earth's leaders understood this all too well, and they were not patient. From the cramped communications hub of MOSF, dispatches arrived daily from the Interplanetary Energy Commission, formal requests worded as urgent recommendations. The tone had sharpened in recent months, edging toward demands. Increased throughput, reduced downtime between harvest cycles, divert more fuel shipments from Mercury's own reserves. The Mercury colony's leadership pushed back, citing engineering limits. Magnetic trap maintenance was not something to rush. Superconducting loops stressed by overcurrent could quench catastrophically, vaporizing cryogenic lines in seconds. And the proton stream itself had rhythms, intensities that rose and fell with the sun's moods. Push the traps too hard during a low cycle, and the efficiency plunged, wasting both power and material. Still, Earth's view was simple. More helium-3 meant more power, and more power meant stability. Politicians invoked the image of glowing cities and climate-controlled greenhouses fed by the clean fire of fusion, images that played well in election cycles and news feeds. Few spoke publicly about the cost of rushing the process, or about the fragile orbital mechanics that kept MOSF balanced in a corridor between the sun's radiation pressure and Mercury's gravitational tug. In a conference room suspended along one of the station's outer rings, the weekly Earth-Mercury liaison call had begun. Commander Liz Solarin sat among a dozen specialists, the ring's rotation lending a gentle half-gravity that kept coffee cups obediently in place. A wall-sized display streamed the faces of Earth-based delegates, their backgrounds showing lush blue skies or polished offices. Whether real or generated, Liz couldn't tell. "Commander," began Chairwoman Halden of the Commission, her voice smoothed by latency filters, "your last report shows a 12% drop in net capture rate for the past 5 days. Can you confirm this is due to equipment downtime, and not operational policy?" Liz kept her tone even. "The drop corresponds to variations in the proton flux. Our traps are operating within optimal parameters. Pushing beyond those would cause net loss. Your definition of optimal may differ from ours," another delegate cut in. "The terrestrial grid is approaching critical deficit. This isn't merely an engineering matter, it's humanitarian." The word hung in the air. Humanitarian. As if the people of Mercury and its orbit were somehow outside that definition. Liz gestured toward a secondary display, where a live readout showed the solar wind data. "We're monitoring anomalies in the proton stream. Until we know their source, we can't adjust capture fields without risking trap stability. You asked for sustained output, we can only sustain what the sun delivers." There was a pause, the kind that meant the Earthside team was checking notes, perhaps weighing how far to push. Finally, Chairwoman Halden's image leaned fractionally forward. "Commander, I'm authorized to inform you that the Commission is considering direct intervention. A supplemental crew from Earth could assist your engineers." In the muted light of the conference ring, Liz felt the room shift. Such an assistance mission would bring Earth's oversight directly aboard, along with the political pressure to bypass safety protocols. It would also mean the colony's autonomy, hard-won over decades, would be compromised. She answered carefully. "We'll take your proposal under review. But I must stress, altering operations without full understanding of current proton stream behavior could threaten not just output, but the stability of our orbital position." The call ended with formalities, but the tension lingered long after the displays dimmed. The crew returned to their work, moving with the measured pace that came from years of living close to the sun outside. The collectors drank in the solar wind, each magnetic loop curving space just enough to guide the protons home. For now, Moss's Helium-3 output flowed steadily toward Earth, each shipment a promise and a warning. The planet's hunger was vast, and the sun's patience was finite. Somewhere between those truths, the station kept its silent vigil. Chapter 3: Proton Storms. The sun was never truly still. From the vantage of Mercury's orbit, its surface was a shifting ocean of light and plasma, currents of searing hydrogen, arcs of magnetism twisting like cosmic ropes. Most days its wind was steady, predictable in its turbulence. But sometimes the sun exhaled harder. The phenomenon was called a solar proton event, or more simply, a proton storm. At its heart lay the sun's tangled magnetic fields. As these fields reconfigured, snapping, reconnecting, and releasing pent-up energy, charged particles were hurled outward at extraordinary speeds. Protons, stripped bare of electrons, could reach the inner solar system within hours. On Earth, these storms were softened by a blanket of magnetosphere and atmosphere. Here, just outside Mercury's embrace, there was no such shelter. The Mercury Orbit Solar Farm lived and worked inside the raw stream. Early signs. In the Control Rings Observatory, a wideband solar monitor traced the sun's behavior in real time. Flares brightened briefly on its surface, their loops arching higher than Earth's diameter. Spectral analysis showed subtle but worrying changes: a widening in the proton energy distribution, a small shift in the peak velocity. Liz Solarin stood beside the display, arms folded, listening to Dr. Elias Rinn, the station's chief astrophysicist. He spoke in a voice as calm as if he were describing a painting. "Coronal mass ejection from active region 4321, he said, pointing to a magnetic knot unfurling near the sun's equator. "It's small, but the embedded fields are directed toward us. We'll see an uptick in flux within 14 hours, maybe sooner if the front edge is fast." Liz studied the projections. A ribbon of color showing particle density rising steadily, climbing toward levels the traps had never handled for more than a few hours. "And the irregular pulses we've been recording?" she asked. Rinn nodded slowly. "Likely precursors. The sun's been breathing in short bursts, pushing high-energy protons ahead of the main front." Storm physics quietly told. The station's design could handle fluctuations. Its magnetic loops had dynamic control systems that adjusted field strength in milliseconds. But storms were different. The problem wasn't just the quantity of protons, it was their energy. High-energy protons could penetrate deeper into shielding, causing electronic upsets and single-event damage to memory circuits. When they entered the trap fields at excessive velocities, they didn't settle into gentle spirals. They ricocheted, scattering particles already stored, creating losses instead of gains. Worse still, the loops themselves could be stressed. The superconducting cables operated at cryogenic temperatures, and surges in particle energy increased inductive heating. If the temperature rose above the critical threshold, the material would quench, transitioning abruptly to a normal resistive state. In the vacuum of space, a quench wasn't just a shutdown. It was a violent release of stored magnetic energy, enough to vaporize cooling lines and cripple an entire collector wing. Rinn explained all of this in the same unhurried tone, as though the science itself was reassurance. "If we scale back capture during the storm's peak," he concluded, "we'll protect the loops and retain most of the stored protons." "And if we don't?" asked Liz. "Best case we lose efficiency for weeks. Worst case we lose a loop. Possibly more." The human variable. That same hour, Earth's message relay delivered a priority transmission from the Interplanetary Energy Commission. The storm had not gone unnoticed there. monitoring satellites around Earth had flagged the same solar activity, but the tone of the message was different. Given current energy deficits and projected supply gaps, all fusion fuel suppliers are instructed to maintain maximum feasible output. Proton event mitigation must be balanced against urgent planetary needs. Liz read it twice, her jaw tightening slightly. Balanced, she muttered, as if the word had been chosen to imply compromise where physics allowed none. The Colony Council gathered in the shielded chamber at the station's core. Its thick composite walls dampened radiation enough to serve as both meeting hall and safe room. Wren presented his forecast, a moderate to strong proton storm, peaking for 4 to 6 hours, trailing effects for 2 days. The safest course was to partially close the traps during peak flux, reducing heating and protecting stored helium-3. Some argued for taking the risk. Earth's grid is in rolling blackout, said Counselor Mira Anwin. If we cut output now, the political fallout could be worse than the storm. Liz countered with measured calm. If we damage a loop, there will be no output for months. Politics won't matter if the traps are dark. The first gust. Even before a decision was finalized, the storm announced itself. The station's external particle counters began to click upward, not literally but in a rapid-fire stream of digital counts. Green indicators shifted to amber as the first front washed over the collectors. From the observation blister, the sun looked unchanged, its brilliance unwavering, its surface unmarked by distance. But the data told another story. The proton density was climbing, the energy spectrum broadening. Wren's voice came softly over the comms. This is just the leading edge. We still have time to adjust. A fragile balance. Adjustments were not simple switches. Each loop's magnetic field had to be tuned so the incoming protons curved into tighter orbits without overloading the field coils. Too strong and the loops would quench. Too weak and the protons would slingshot through, striking containment walls. Technicians in half-gravity worked in pairs, moving with unhurried precision, keying in revised current profiles. Liz moved between stations, her presence steadying the younger crew. The hum of the superconductors deepened slightly as the field shifted, the sound a low heartbeat through the structure. Outside, the storm grew. Protons struck the collector's magnetic sheets, their impacts invisible but measurable in subtle vibrations. Tiny eddies formed in the stored proton clouds, swirling like slow storms within storms. The helium-3 synthesis chambers downstream registered a minor drop in yield, acceptable for now. The waiting game. Proton storms were rarely abrupt ends or beginnings. They were swells in a cosmic tide, their peaks and troughs only partially predictable. The crew settled into a quiet rhythm. Monitor, adjust, log. Liz kept one eye on the proton spectrum, the other on the cooling system's temperature deltas. Through the station's long windows, Mercury itself gleamed far below, a mottled crescent sliding beneath them. The sun's glare outlined every ridge and crater in stark relief. Somewhere on its scorched surface, automated mines continued their slow harvest of metals, their operators oblivious to the storm in space above. The first 4 hours passed without a quench. But Wren's forecast still held. The main body of the storm was on its way. And beyond the rising particle counts lay an unanswered question. The irregular pulses in the proton stream had started before the storm, and they were still there, buried under the surge. Something was shaping the wind in ways they had yet to understand. Chapter 4, Technical Failure. The first hours of the proton storm had been manageable. Numbers climbing, adjustments made, efficiency slipping only slightly. But the sun's wind had a way of hiding its true strength until it was upon you. By the 9th hour, the density curves on Dr. Wren's display bent upward in a near vertical line. The storm's front had deepened, compressing layers of plasma until they traveled as a single high-energy wave. Every collector loop on the Mercury orbit solar farm felt it. Rising heat. The superconducting cables that formed each loop's spine were bathed in liquid helium, chilled to temperatures a fraction above absolute zero. That chill was the key. At those temperatures, the cables carried vast currents with zero electrical resistance, holding magnetic fields strong enough to steer streams of protons. Now, as the particle energy surged, inductive heating began to creep through the system. It was subtle at first. A degree here, a fraction there, recorded in the cryogenic sensors like whispers in the static. Loop 6 is up 3 degrees Kelvin from baseline, reported technician Orrin Vale, voice steady but quieter than usual. still within safety margin but climbing. Liz glanced at the board. The amber indicator for Loop 6 glowed faintly among a grid of green. Start a staged cooldown. Bring helium flow to 90%. Vale tapped the commands. Pumps deep within the collector arm hummed louder, pushing more coolant through channels thinner than a human hair. On the display, Loop SIX's temperature curve slowed, then leveled, temporarily. The pulse returns. Amid the storm's constant roar of data, counts per second, particle spectra, thermal readings, Ren spotted a familiar signature. Buried under the general noise, faint but distinct, the irregular pulses in the proton flux were still there. He pulled the data onto a separate display, isolating it from the raw stream. The pattern was undeniable. Short bursts of slightly higher density at regular intervals, like a heartbeat overlaid on the storm. This isn't solar turbulence, he murmured. It's coherent. Liz looked over. Meaning? Meaning, Ren said, something is modulating the proton flow. Artificially, or through a process we don't yet understand. There was no time to pursue the mystery. The storm itself was demanding every hand. System load. By the 12th hour, 2 more loops, 3 and 9, showed rapid heating. Loop 3's current draw began to oscillate unpredictably, a sign that its field was struggling to maintain stable containment. Compensating with Loop 4, said Senior Engineer Mara Cho, fingers moving over her console in smooth arcs. She was already rerouting part of Loop 3's capture field into its neighbor to stabilize it, but that meant Loop 4 would now be running closer to its own safety limits. The Helium-3 synthesis chambers downstream were also showing strain. Their reaction vessels, where collected protons were gently coaxed into pairing with deuterium, relied on precise energy balances. The storm's high-energy protons arrived hotter than usual, requiring more moderation before they could be used. Moderation took time, and time meant throughput dropped. First failure. At hour 13 it happened. A sharp alarm cut through the low hum of the control room, a tone reserved for quench detection. Loop 9's superconducting cable had crossed its critical temperature. In less than a second, the magnetic field collapsed, and the stored energy in its coils discharged into the surrounding structure. The event was invisible from the outside, but the crew felt it as a deep, muted thud through the station's frame. Sensors registered a spike in local temperature, followed by a drop as the emergency venting system blasted the loop's remains into space to prevent secondary damage. Loop 9 was gone. Damage control. In the sudden absence of its magnetic field, protons that would have been guided into containment spilled outward. Some were intercepted by neighboring loops. Others slammed into containment walls, producing bursts of secondary radiation. Automated shutters sealed off the affected arm, halting both collection and processing there. Ren's voice was calm but clipped. Flux redistribution will push loops 7 and 8 into the red if we keep full capture. Liz nodded once. Reduce capture by 20% across the board. Prioritize loop stability over yield. The order was the opposite of what Earth had demanded only hours before. It would mean fewer shipments, less fuel, and more political fallout. But it would keep the station alive. The human factor again. Minutes later, a tight beam message arrived from the Interplanetary Energy Commission. No video this time, just text scrolling across the secure channel. Reports of output drop already reaching terrestrial media. Unauthorized operational changes are in violation of supply agreements. Resume full capacity immediately. No mention of the quench, no acknowledgement of the danger. Just the insistent pull of a planet's desperation. Liz closed the message without comment. The crew didn't need to see it. Holding the line. For the next 3 hours, the station held at reduced capture. Magnetic fields thrummed at their adjusted strengths, the deep bass of superconducting currents vibrating faintly through the hull. Coolant pumps ran at maximum safe speed, their cryogenic vapors drifting into the vacuum outside like pale ghosts. Even so, small failures accumulated, sensors going offline from radiation hits, minor breaches in containment chambers sealing automatically. Each one was logged, each one adding to the list of repairs that would follow the storm. By the 16th hour, the storm's peak finally passed. Proton density began to drop, though the pulses, those strange, regular surges, remained. The crew could breathe again, but only just. They had survived the worst of the storm, but at a cost. A collector arm was gone. Output had been cut. and the questions about those pulses were growing sharper. Chapter 5. Orbital Safety Breach. The storm was easing, but the station's relief was short-lived. In the quiet after the proton surge, the MAS's instruments began reporting a different kind of anomaly, one that had nothing to do with the sun's natural rhythms. A subtle drift. Orbital mechanics were the hidden heartbeat of every object in space. The Mercury orbit solar farm followed a carefully tuned path, a stretched ellipse that skimmed just inside the planet's Hill sphere, balanced between solar radiation pressure and Mercury's weak gravitational pull. That path was no accident. It was calculated so the massive collector wings could sail on the solar wind, using their magnetic fields like tethers to the sun's invisible streams. Now, telemetry from the station's navigation suite showed a slow, steady drift off its intended trajectory. The change was small at first, millimeters per second in velocity almost beneath notice, but over hours it would grow, and over days it could shift the station into a dangerously unstable path. The physics of the threat. Dr. Rin explained it in his unhurried way, voice level, eyes scanning graphs. When the collectors operate at reduced capture, he said, the balance between magnetic drag and radiation pressure changes. Normally, the excess push from the sun's light is cancelled by the pull of our magnetic traps on the proton flow. But after the quench in loop 9, our symmetry is broken. One arm missing meant an uneven distribution of magnetic force. The station was effectively being pushed more strongly on one side than the other, like a sailboat with one wing torn away. The result was a slow yaw and a drift outward from the stable corridor. In deep space, a drift like this could be corrected with thrusters. But here, so close to the sun, the timing was critical. Every maneuver had to counter both gravitational and radiative forces without overtaxing the station's limited propellant reserves. The pulse pattern again. Navigation logs revealed something unsettling. The mysterious proton pulses were coinciding with slight fluctuations in the station's drift rate. Each pulse, small as it seemed, exerted a measurable kick on the magnetic collectors. The effect was cumulative, like a steady push every few minutes, always in the same direction. Ren's conclusion was cautious but clear. If the pulses are natural, we've discovered a new kind of solar behavior. If they're not, he let the sentence hang, the implication needing no voice. Liss studied the plotted course corrections. If they're not natural, someone knows exactly how to push us out of our lane. Earth's reaction. The Interplanetary Energy Commission had no interest in orbital mechanics, at least not as long as the fuel kept coming. Their latest message was as terse as the last. Storm has subsided. Resume full capture immediately. Failure to comply will trigger review of autonomous status. There was no mention of the drift. Either they hadn't been told or they didn't believe it was relevant. To them, the crisis was the drop in Helium-3 output, not the possibility of a billion-ton station veering into an unsafe orbit. The risk of loss. Rin brought up a simulation on the main display. In it, the station's projected path curved away from Mercury's shadow, into a sunward arc where the collectors would be directly exposed to the full brunt of solar radiation without the buffering of the planet's partial eclipse. Temperatures would rise, cooling systems would strain, and the superconductors, already stressed, could fail en masse. Beyond that, the drift could intersect with the orbital highways used by freight haulers between Mercury and Earth. Even a glancing collision in that zone would scatter debris along a path that would take years to clear. 2 paths forward. The council assembled again in the shielded chamber. On the table were 2 choices, each carrying its own price. Option 1. Divert significant power from capture operations to the station's ion thrusters, using them to counter the drift. This would mean having Helium-3 production until the orbit was restabilized, an unacceptable delay in Earth's eyes. Option 2. Keep capture fields at full strength and try to steer, using asymmetric adjustments to the active loops, effectively sailing the proton wind like a ship in a shifting current. It was a delicate maneuver that could save production, but it relied on stable storm conditions, and the pulses made that stability unlikely. Deliberation. Voices in the chamber were calm but firm. Counselor Anwin leaned toward the second option. If we keep the collectors in play, we preserve output and autonomy. We've navigated solar wind differentials before. Mara Cho shook her head. Not with a loop down. We'll be trimming with one hand tied, and those pulses will make it impossible to predict the force on each wing. Liss listened without interrupting, eyes on the orbit simulation. She saw the sunward arc narrowing, the margin for error shrinking with each pulse. The risk wasn't just to the station, it was to every vessel sharing the inner system's transport lanes. The decision. Finally, Liz spoke, her voice as steady as the low hum of the station's superconductors. We hold the line on safety first. Reduce capture to 70%, divert surplus to thrusters. If we can't keep our orbit, there's no point in filling the tanks, we'll lose the station. The council voted, the motion passing by the narrowest margin. Orders were relayed to the control ring. In the navigation suite, ion thrusters lit in a faint blue haze, their exhaust streaming sunward, invisible except in ultraviolet. The drift slowed, then stopped, though the pulses continued their steady beat. For now, the station was back in its lane. But in every mind present was the unspoken truth. Something out there was pushing on them, and no one yet knew why. Chapter 6. Decision on the Edge. The station had stabilized its orbit, but the cost was visible in every metric. Helium-3 output had fallen to barely 2/3 of pre-storm levels. The Interplanetary Energy Commission's messages had shifted from clipped orders to what could only be called ultimatums. And the pulses, they had not stopped. Patterns in the noise. In the quiet after the storm's peak, Dr. Wren pulled together the cleanest data sets, readings from before, during, and after the Proton surge. When stripped of background fluctuations, the pulses emerged in sharp relief. Bursts at precise intervals, each lasting exactly 0.72 seconds, separated by a gap of just under 4 minutes. Natural solar processes were rarely so regular. Magnetic reconnection events, coronal waves, and solar wind density fluctuations all had rhythms, but they were fractal, imperfect, shifting over time. This was metronomic. Wren's simulation suggested each pulse was altering the magnetic topology of the solar wind upstream of the station's position, nudging proton streams just enough to push on the collectors, and occasionally spilling particles at energies ideal for helium-3 synthesis. In other words, whatever caused the pulses wasn't merely disruptive. It was tuned to the station's operation. Theories carefully spoken. The council assembled once more. Wren presented his findings in the chamber's muted light. Possibilities fall into 3 groups, he began. 1. A rare, naturally occurring solar oscillation, previously unrecorded. 2. An artifact of our own systems, perhaps a feedback loop between collectors and the surrounding plasma. 3. He paused. Deliberate modulation from an external source. Liz leaned forward slightly. External as in, another installation? A vessel? Wren's gaze didn't waver. Or an automated probe. Something positioned sunward, close enough to influence the wind before it reaches us. Counselor Anwin exhaled slowly. You're suggesting someone shaping our feet. For what purpose? To force output up or down, at will. Possibly to destabilize our orbit. Earth's last push. Before the council could settle on a course, a live transmission arrived from Earth. Chairwoman Halden herself, flanked by 2 stern-faced advisors. Commander Solarin, Halden began, her tone almost cordial. We have reports of significant reductions in fuel output. The Commission requires full restoration within 72 hours. If the station's leadership cannot guarantee this, we are prepared to assign supplemental oversight personnel. There was no mention of the pulses, the drift, or the quench. Only the schedule. Liz kept her voice level. We can restore output by pushing the collectors harder. But that will leave us no margin for orbital corrections if the pulses worsen. Halden's response was immediate. That is an operational risk we are prepared to accept. Liz didn't reply right away. In her mind, the words translated to, it's a risk we are prepared for you to take. The edge of control. In the control ring, engineers ran projections. Operating at full capture in the current conditions would require asymmetric field boosts to compensate for the missing loop 9. That meant tolerances so narrow that a single unexpected pulse could unbalance the array, forcing emergency shutdowns, or worse, cascading quenches. Mara Cho, the senior engineer, voiced what no one wanted to say aloud. If a quench chain starts, we could lose half the array before we stabilize. That's months, maybe years, of recovery. Liz stood at the central console, one hand resting on the railing. Around her, the low vibration of the superconductors was a physical reminder of their limits. She weighed the equations against the politics, the safety margins against the lights going out in cities she had once called home. The choice. She called the council to a final, private session. The options were stark. Yield to Earth's demand, push the collectors to maximum, risk orbital stability and hardware integrity, and hope the pulses didn't align with a critical stress point. Defy the order, hold output at reduced capacity, maintain safe margins, and risk losing the station's autonomous status, and possibly control of its mission entirely. Silence hung in the chamber. Finally, Liz spoke. We've seen what the sun can do when it decides to remind us who's in charge. I won't give it the opportunity to take the whole array because we were afraid to say no. A slow round of nods followed. The vote was nearly unanimous. Reduced capture would continue, thrusters would remain active, and Wren would begin triangulating the source of the pulses. Preparing for the peak. Back in the control ring, adjustments were made quietly. Magnetic field strengths were capped, power budgets redistributed. Ion thrusters maintained their gentle push against drift, their blue haze invisible to the naked eye. Liz took one last look at the sun through the observation blister. Its brilliance was undimmed, its face unchanged. But somewhere between its seething corona and the station's magnetic petals, something was tapping at the wind with a steady, deliberate rhythm. The decision had been made. Now they would have to live with it. Chapter 7. Sunrise over the Sun. The pulses had been counted, catalogued, and mapped against the station's orbit. Each burst arrived from a fixed direction, sunward and slightly above the plane of Mercury's path. Dr. Wren's triangulation placed the origin within a narrow cone of space, a corridor so close to the sun that no unshielded human craft could survive for long. The observation window. The next pulse window was less than 2 hours away. Liz ordered a temporary reconfiguration of the collectors. Several loops were rotated out of their usual alignment to serve as giant magnetic lenses, focusing their fields not for capture but for imaging. At the same time, an ultraviolet interferometer, normally used for monitoring coronal structures, was repurposed to sweep the origin zone. The station's rotation was slowed fractionally to give the instruments a longer look. As the glare of the sun filled the sensors, the usual haze of charged particle noise gave way to a faint geometric outline, 3 narrow arcs, nested like the ribs of a sail. An engine in the wind. Wren's voice was quiet but certain. That's no natural formation. The arcs were the leading edges of magnetic sails, each 1/10 of kilometers across, shimmering in the proton flow. The sails' alignment matched the pulse rhythm exactly. They were flexing in and out of the wind, shaping and compressing the proton stream before it reached MOSF. The object they were attached to was small by comparison, a central hub no larger than a shuttle. It carried no identifying transponders, no communication signals. Its orientation was fixed toward the sun, as if drinking from the same wind that powered the station's harvest. Purpose and possibility. Wren's analysis came in steady sentences, even as the implications deepened. They could be here to pre-process the wind, increasing helium-3 yield at the cost of stability. Or they could be using our collectors as a downstream proof of concept, testing how their sail control affects a large-scale array. Counselor Anwin asked the question they were all thinking. And if the pulses we've been seeing are intentional destabilizations? Wren hesitated only a second. Then this is not an experiment. It's leverage. The tuning moment. The next pulse was due in 12 minutes. Liz saw an opportunity. If they could rephase the active loops at the exact moment the sail flexed, they might either nullify its push or, if her engineers were right, steal a fraction of its concentrated proton stream. Mara Cho stood over the capture controls, every adjustment cued but held in standby. Around the ring, the crew moved with a precise stillness, eyes on their displays. The countdown reached 0. The pulse came, a compression of the proton wind that hit the collectors like a silent wave. At that instant, Mara executed the rephase. Magnetic field lines shimmered invisibly, their curvature shifting just enough to catch the extra energy. The surge. Readouts leapt in unison. 420 seconds, helium-3 production spiked to levels no single loop had ever reached. Containment remained stable, temperatures held within safe bounds, and the drift from asymmetric force was almost nil. Then the pulse faded. The sails beyond the sun's glare stilled, as if the source had felt the station's change in response. What was gained? When the numbers were tallied, the single intercepted pulse had yielded nearly a week's worth of normal output. More importantly, the experiment proved the station could ride the pulses rather than be pushed by them. turning an unknown influence into a potential ally. But the sails were still there. Whoever had placed them had not moved, had not sent a signal, had not claimed responsibility. Liss looked at the final line of Wren's report. The wind is not ours alone. Dawn over the sun. As the station rotated back to its standard orientation, the sun rose over Mercury's horizon, a blinding arc that painted the collectors in gold. The Helium-3 tanks were fuller than they had been in weeks. The orbit was stable. The mystery was deeper. Liss stood in the observation blister, her reflection merging with the mirrored glare beyond. Somewhere in that light, another presence was shaping the same wind they depended on. For now they could work with it. But the next sunrise would bring the next pulse, and with it the question of who, or what, was sharing the harvest. Epilogue, quiet victory. The station moved in its measured arc, balanced once more between the pull of Mercury and the push of the sun. Inside the collector arms, the hum of superconducting loops was steady, almost like a distant ocean in the walls. The cryogenic lines sang in faint harmonics as liquid helium flowed through them, keeping the fields sharp, the traps cool. Helium-3 production had returned to a rhythm, not the frantic pace Earth demanded, but a sustainable flow, unbroken by quenches or sudden drops. The tanks filled slowly, their silvery cargo locked away in magnetic bottles until the next transfer run. The unanswered presence. The magnetic sails beyond the sun remained. They had not pulsed again since the day MOSF caught the wind and turned it to its advantage. Whether that was a pause, a retreat, or simply a change in whatever schedule guided them, no one could say. Wren kept a quiet log of their position estimates, plotting the faint shifts in reflection angles that the sail's edges betrayed. Liss didn't ask for daily updates. Some mysteries could wait until they chose to reveal themselves. Earth's voice quieter now. Messages from the Interplanetary Energy Commission were still sharp-edged, but less frequent. The last transmission had been an acknowledgement of the station's stabilized throughput and a reminder of shared responsibility to the grid. The threat of supplemental oversight had faded, for now. The crew understood that politics, like orbital mechanics, was never static. Pressure would build again. But for the moment, the silence was welcome. A view at dawn. On Liss's off-shift, she walked the spine to the forward observation blister. Mercury was a dark curve below, its craters dusted in faint silver where the sun's light grazed them. Above and beyond, the sun burned with the same indifferent brilliance it had for billions of years. Somewhere between that star and this station, invisible rivers of charged particles flowed past, carrying the raw material for 1,000 futures. Some of those futures would be built on trust, others on competition. The wind did not choose, it only moved. The last thought. As the next pulse window approached, the collectors adjusted by fractions of a degree, their vast petals catching the morning's invisible tide. Liss rested her hands against the railing, feeling the station's faint vibration through the metal. The sun would rise again tomorrow. The wind would come. And they would be here, listening, catching, learning. In the quiet heart of the solar wind, that was victory enough. Thank you for gliding through the aurora-lit arc of elemental science fiction here on Night Chemistry. May undiscovered elements settle kindly in your thoughts, and may distant suns arrange themselves into calm constellations of dream. Until our next voyage beyond the periodic dawn, sleep well and good night.